I found an interesting puzzle in Matt Parker's Maths Puzzles, and it's called How Odd is Pascal's Triangle? So basically the actual question is what percentage of Pascal's triangle are odd numbers? That is for the first 128 rows. Yeah. So you can try answering this yourself, and then I'll move on to explain. The first question you should be asking yourself when you're trying to solve this problem is, what do the odd and even numbers in Pascal's triangle look like? So I'm going to do this, so let's see. So I'm going to this here, and then now I'm just going to write out Pascal's triangle. So 1, then it's 1, 1, then it's 1, 2, 1, and it's 1, 3, 1, and I'm just going to quickly go through the first few rows. So now that I've written out the first 10 rows of Pascal's triangle, I'm going to convert it to just odds and evens. So every odd number I'm going to have an asterisk, and every even number I'm just going to put a blank space. Now that I've got the Pascal's triangle converted to just asterisks and spaces, now we can see what it does. So first I'm just going to move all this triangle into just one space there. That's easy to look at. And then, so first you might notice that there's some rows which are all odd. And you can also see here there's the 2 1s, there's 1 3 3 1, and then there's this row, number 7, 1, 7, 21, they're all odd. And then you also might notice there's these mini triangles that kind of form in here. And if you're really experienced, then you also might notice that this is the Sierpinski's triangle. So it's just made when you start with a triangle and then you start cutting triangles into it. And yeah, this is just a different version of Sierpinski's triangle made out of, and the odds are just the borders of the Sierpinski's triangle, and the evens are the white spaces. And now we can also inspect, so every odd number and an even, so an odd number and an even number, so for example here, it's always going to generate an odd number. But then if there's 2 evens, or if there's 2 odds, it's always going to generate an even number. So you can just see that, if you get an alternating row of odd, odd, even, odd, even, odd, even, odd, then it's going to turn into a whole row of odds. But then a whole row of odds is just going to turn into one odd number on either side, and then a big even space in here. And why these triangles form is because of the way that it behaves. So because odd and even make an odd, so that's why this kind of just starts going like inwards, in. So it starts going inwards, and then this space is always even because 2 evens make an even, so you just get this big, so once you've got one big white space, you keep getting white spaces, but it slowly gets smaller. And you can continue this, and this will actually be, what do you call it? I think symmetric or something. No, I forgot the term for it. It just means that you can just find it repeated sections of it. So you can actually find this piece is also here, and it's also here. Or you can also say that it's just this is a smaller piece, that this top triangle with the first 4 rows is just a scaled down version of this big triangle of the first 8 rows. The next thing we need to do is count the number of odd numbers in each row, because that's exactly what we're trying to find, number of odd numbers in each row. So let's go. 1, 2, 2, 4, goes back down to 2, 4, 4, 8, goes to 2 again, then 4 and 4, and this continues. And just to get a better view of this and more detail, I'm going to continue it for another few rows. Now I've added way more rows, as you can see, and also these numbers here, and I just listed them down. And now you can actually start looking for patterns. So what I noticed is that, look, there's 1, 2 right here, then 2, 4 is just doubling both of those numbers. Then if you get 1, 2, 2, 4, then double that, you get all those numbers, you get 2, 4, 4, 8. And that pattern continues. You double all of this section, then you get all of this section. And if you double all of this section, you're gonna get, if I continue this just this section doubled up. And so this is actually very important to notice, because then you can find that every time you double the number of rows, you triple the number of odd numbers, because this section is just going to be, so this is going to be 3, then this, whatever this is going to be double that. So double that, so it's 6, and then if you add them together, you get, and if you add them together, you get 9, which is triple of 3. So when you double the rows, you triple the number of odd numbers. This is actually a really important thing to realize, because now we can just basically solve the puzzle, because we asked for the first 128 rows, and 128 is the same as 2 to the power of 7. So we know that we have to double the number of rows 7 times. And if we double the number of rows 7 times, then we have to triple the number of odd numbers 7 times. So we get 3 to the power of 7 odd numbers. So, but we're still not done yet, because we were asked for the percentage of odd numbers out of the whole triangle, and we've only given the number. So now let's find the percentage. All we have to do is just find, so there's 128 rows, and then if you know how to find triangle formula, it's just n plus 1 over 2. It's just the formula for finding triangular numbers, and we need to plug 128 into this. So 128 times 128 plus 1 over 2 is the same as 64 times 129. And if you get a calculator out and do it, it'll be equal to 8,256. Now we just have to divide 3 to the power 7 by 8,256. So 3 to the power of 7 is the same as 2,187. So it's the same as 2187. Then you just have to divide that by 8256, and then you'll get approximately 0.265, so which is 26.5%. So now I've got a graphing calculator out, and you can actually see that this starts to approach 0. Yeah, if we can zoom out a bit. And remember, this isn't just the first x rows, this is the first 2 to the power of x rows. So yeah, just don't get that confused. And then you can see that it clearly approaches 0. And if we want to, we can just zoom right in. So negative 0.001, that'll be fine, and then this will be 0.001. And there we can see. So okay, we should be zooming out a bit more. So this can just be -1, that will be good enough, and then this will be 100. It's been there. So you can clearly see that it just zooms straight down to 0. And if you zoom back out again, and yeah, I'm going to move that back to normal. It actually makes a nice, like, it looks kind of like a bell curve. I'm not too sure this actually is a bell curve function though. Yeah. And so it approaches 0 quite quickly, or maybe not that quickly, because remember, we're counting exponentially. So if you're asking the question, what percentage of the whole Pascal's triangle are odd numbers? Your answer, 0%. But you might say, wait, why would it be 0? There are clearly odd numbers in the Pascal's triangle, and there are odd numbers in every row. It's true. This is true, but if you've got infinite numbers, then you've got an infinite number of even numbers, that is a more infinite number of even numbers, like a higher, so like more even numbers, so way more, so that it converges to 0. So yeah, if you're asking any finite number of rows, then it won't be 0. But if you ask for the whole Pascal's triangle, which is infinite, then you just get 0. I also want to relate the fact that the odd numbers in Pascal's triangle goes down to 0, and how Sierpinski's triangle is generated in this way. Because every time we add a new triangle in, like a new level in, we decrease the area by 3/4. So down by 3/4, down by 3/4, as you can see. Then this keeps going on, and so it actually, because this is a fractal and it goes on infinitely, this happens infinitely many times. But if you multiply any number by a number less than 1 infinitely many times, then you're just going to get 0. And with our Pascal's triangle example, the white spaces are even and the black spaces are odd, so the area is just going to converge down to 0. So yeah, this is a really nice explanation of why this happens. So thank you for watching, and I'll see you